In this video on covalent bonding, we're going to especially look at bond polarity. You can see in the pictures, these diagrams represent where electrons are. In a totally covalent bond, we call that a non-polar covalent bond, the electrons exist between the two nuclei. In a polar covalent bond, more electrons are held closer to one nucleus than the other. This is the polar covalent, and if the electron is completely ripped off and given to another atom, we actually have ionic bonds, and that's what we've just studied. Covalent bonds are made when two non-metals work together to achieve an octet on their valence level. Remember, an octet means 8 electrons, which is a full outer shell. The exception would be 2 electrons for hydrogen, and an exception we'll work on later is 6 electrons for boron. These are the only exceptions that we'll use to the octet rule. They do this by sharing electrons. It's just like your parents both get to claim you as their child. You're not being double counted, you just have 2 parents. Now, that's what that says. Let's look at this. In this case, you have hydrogen with 1 electron on its outer layer, and oxygen with an outer layer that has 6, not 8. When they come close together, they orbital overlap, meaning they put their orbitals together, and they share these 2 electrons. 2 electrons is considered a single bond. And oxygen does this twice, so with 2 separate hydrogens, to get an octet on its outer level. Let's double check and make sure that's what's happened. 1, 2, 3, 4, 5, 6, 7, 8. So 8 electrons. Hydrogen has 2 electrons each on its outer layer. It's only got the 1 s, so it only can have 2. So each of these has reached a noble gas electron configuration, or a full outer shell, if you will. In this case, these 2 atoms are sharing a total of 4 electrons. When you share 4 electrons, it's a double bond. By sharing 4, each atom now has 8 in their valence. So if we do a quick count, all the shared one equals 4. Then let's go to the green. 5, 6, 7, 8. Now to the pink, we have 4 shared. 5, 6, 7, 8. Notice that they each got to count the shared electrons. Let's move over here to nitrogen. There are 6 electrons. That is the most electrons that can be shared. Make a note of that. We call this a triple bond. By sharing these 6 electrons, each nitrogen is getting an octet on its outer layer. Let's count. So 6 in the box, 7, 8. 6 in the box, 7, 8. Remember, these inner electrons, those are not on the valence level, so they are not counted in the octet. So, only the valence electrons are shown because only the valence electrons take part in the covalent bonding. Notice they come together. Chlorine has 8 over here when it forms. Methane, by bonding with 4 separate hydrogens, gets a total of 8 on its valence level. And water, which we've already seen, it needs 2, so the 2 hydrogens come in. So let's look at the formation. The bond itself is shared electrons between the 2 nuclei. It's held together because the 2 nuclei are electrostatically attracted to the negative charges, the electrons, that are between them. So this nucleus here is attracted to both of these electrons. This nucleus over here is as well. There is some nucleus-nucleus repulsion, but the attraction is greater than the repulsion in this case, so they stay together. Now, are all electrons shared equally? Sometimes. An atom with a stronger electronegativity, and maybe I should say greater electronegativity, will pull the shared electrons closer to itself. When unequal sharing occurs, it is a polar covalent bond. Be very, very careful. Last year you talked about polar covalent molecules. We haven't gotten there. This is a polar covalent bond. If electrons are shared equally, then you have a nonpolar covalent bond. So let's look at this chart. In the sharing, if they're equal, it's nonpolar covalent. The electrons are located almost exactly between the two atoms, kind of right in the center. You can see on this picture, the two shared electrons are right in the center. They're equidistant from each nucleus. We're going to look at electronegativity differences in a moment, but any electronegativity difference of 0 to 0.3, sometimes people fudge to 0.4, so just be careful. You're going to want to judge based on the location on the periodic table. That is a nonpolar covalent bond. Unequal sharing is a polar covalent bond. The electrons can be found near the most electronegative atom. Our differences will be about 0.3 to 2.0. You're going to judge based on the periodic table, and just remember, no metals. So even if you get a difference less than 2.0, that doesn't make it covalent. It's definitely ionic. What we have here are the electrons living closer to this chlorine atom. Therefore, this side of the atom becomes a partial negative. This is a lowercase delta. It's almost like you make a figure 8 and stop, and a minus sign. That's indicating that the chlorine atom is more negative than the hydrogen atom because it's a partial positive. So one side of the bond takes on a partial negative charge, that's the chlorine, and the other a partial positive charge because electrons are located closer to the chlorine. Notice there's none of that in the nonpolar covalent because there's no partial charges. Now let's use the chart of electronegativity to determine the differences, which will give us the bond polarity, whether it is polar covalent or nonpolar covalent. The general scale is 0 to 0.3, and I say ish, it moves, is nonpolar covalent. From 0.3 all the way up to about 2, and that's an ish as well, is polar covalent. And then anything beyond that is definitely ionic. But really, this region right here, up here when you're looking at is it ionic or polar covalent, you really need to look at is it a metal or a non-metal. So look in the metal versus non-metal. Non-metals form covalent compounds, metals do not. Down here, you're just going to want to look at the periodic table. If they're very close together and they're at like 0.3, then they're going to be nonpolar. If they're farther apart, they're probably polar. Don't worry too much about it. Chances are I won't give you a 0.3. So let's see how this works. Sulfur and hydrogen. Sulfur, I'm looking at the chart, is a 2.5. Hydrogen is a 2.1, so I get a 0.4. That means that it is polar covalent. There's two things we now need to do. We need to draw an arrow above the sulfur-hydrogen bond, pointing towards the atom that is more electronegative. So we draw this arrow, it goes towards the sulfur. We put a thing back here to show that it is a vector, and then we make a partial positive, partial negative. This, doing both the partials and the arrow, is actually overkill, but I want you to be able to do both, and I was trying to highlight, and that kind of went horribly wrong, but the partial positive, partial negative, and the arrow. I want you to practice with those. So sulfur and chlorine, 2.5 minus 3.0. Like, oh my goodness, I now have negative. Well, really just take the absolute value. So 0.5. Okay, so it's a polar covalent bond. It's towards the chlorine. So I draw that arrow. And I say that sulfur is now partial positive and chlorine is now partial negative. Number 3, oxygen and chlorine. So oxygen is 3.5, chlorine is 3.0, so another 0.5, so it's polar covalent. This time it's towards the oxygen. Remember, we draw the arrow towards the most electronegative. The side that the arrow is drawn to, and that's supposed to be straight, is the negative side. The other side is considered the partial positive side. Let's go down to bromine and chlorine. So bromine is 2.8, chlorine is 3.0, so 0.2. That's a non-polar covalent bond. We do not draw an arrow for a non-polar covalent bond. You're done with this one. Carbon and oxygen, 2.5 and 3.0. Oh my goodness, 3.5. I messed up the top one above as well. Let's go back. So that's 1.0, and it is polar covalent. So draw my arrow towards the oxygen. I say it's the more negative one, this is the more positive one, and then I'm done. So if I go back up, nope, I got it right. Okay, we'll keep going then. Bromine, bromine. I'm going to let you in on something. Diatomics, or atoms bonded to atoms of the same, will give you an electronegativity difference of 0. So they're non-polar covalent. So notice 2 out of the 6 were non-polar covalent. 4 were polar covalent. The vast majority of bonds are polar covalent. You can kind of see we've got a long area. Something worth memorizing are these 4. Fluorine is a 4.0, oxygen is a 3.5, chlorine is a 3, and nitrogen is a 3. This is the first or the most electronegative. Oxygen is the second most, and chlorine and nitrogen are tied for third. So they're number 3 and 4. What this means is anything bonded with fluorine that's not fluorine will automatically be polar covalent. Anything bonded with oxygen will automatically be polar covalent. These two, we start getting into 3.0, 2.5, 2.8. It gets kind of messy down below it, but these still have pretty high electronegativity. So you can kind of judge. So chlorine's a 3.0, bromine's very close, so I would be hard pressed to figure out, oh my goodness, is it polar or non-polar covalent without doing the math.